We're going to look at now solving systems of equations with three variables. So before we do though, since we already have been working on systems with two variables, you can kind of work through this handout on your own. So you should pause right now and take a few minutes to try and read through page 91 to 92, and try and kind of fill in and see what you think first. Then once you've gone through that, then unpause. Well, now that you've looked through this, let's see if we kind of agree. So it says, when solving a system of equations, what is the solution going to describe? Well, when we had a system of two equations, just a little reminder, when there were two equations, those were both lines. There were two variables and there were lines. So there's a couple different things that can happen. They could meet at one point, or they could never meet at all. So there would be no solution to that. Or they could be that they're the same exact line. And so if that happens, there's an infinite number of solutions. Now for a system of equations in three variables, this is now representing a plane. So you can imagine like a piece of paper. So three equations and three variables ends up looking a little bit differently. So the way that we draw a plane normally is just as a kind of looking like a piece of paper, but imagine that it extends in all directions just like the lines do. So you could have that the three are intersecting each other at one point. So I'm not going to pretend I know how to draw in 3D, but maybe I could try. Nope, fail. But you can imagine that they are all intersecting at one point or one line. So that could happen. You could have where like you have one more horizontal, one coming out at you, and then there's one kind of flat one going through. And if that's going to happen, they'll all intersect at that one point. So what I imagine for that, if you picture in your room, you have your two walls and they intersect at a line, but then where they intersect the ceiling is going to be like a top corner point. So there could be an infinite number of solutions, one solution. You could have where all your planes are parallel to each other, and so there would be no solution. You could even have like two planes being parallel, but then there's one that kind of goes through them all. And again, there would still be no solution because you had two that were parallel. So there's a variety of different things that could happen. But overall, if we're going to get that one point, it's the point, and now we're in 3D, that satisfies all three equations. And most of the time, if you do get one ordered pair, that's the picture that we should be imagining. Now, when solving a system of equations with three variables, you want to try and eliminate a common variable for each equation. So I'm going to number these equations off. So 1, 2, 3, so that way we can still see where they are as we split them apart. So it took equations 1 and 2 together, and then 2 and 3. So why do you think the student chose to separate these two pairs? Well, I think it wanted to use all of them up. And since there's an odd number, you got to put one of them with both of them. So that's why I see 2 repeated. So let's try and see what's going to happen. So we want to reduce the system so it can only contain 2 of the same variables. So what happened here? If we're looking at equation 1, and then this is still equation 2, but it looks a little bit different. What did the student do? Well, you should notice that they multiplied by 2. And on the other set, again, they're taking equation 2 with equation 3 this time. And this time, equation 2 looks different because they multiplied by -2. And so let's see why they chose those numbers. So if we add the equations together, again, that's equation 1 and 2, and this is equation 2 with 3. We're going to end up with, that will be a 5x. The y's cancel, and we'll have 5z equals 15. And on the other side, we'll add up the x's, will get -7x. Again, the y's will cancel. We'll get -4z equals -18. So what we've done, once we add the two equations together, we eliminated y in both pairs. And that's really important that it's the same variable, because now look what happened. We're going to be able to take these two new equations, and it says, what do you think we should do next? Well, we should solve this new reduced system. So it's not that new, it just looks different because we're able to eliminate the variable y. So if you flip over on the next page, it rewrote those two equations. So you can see that it was the 5x plus 5z equals 15 and negative 7x minus 4y equals negative 18. So they're going to try now and solve this. So let's see, they went and they rewrote the equation in this way. Why do you think they did that? Well, it looks like they're trying to eliminate the z's. You could eliminate x's or you could eliminate z's. Maybe they chose this because it's smaller numbers. But they're trying to eliminate one of the variables. In this case, it was the z. So you can see that after adding those two equations together, the x's will add and make negative 15x. The z's will be eliminated. And then the 60 and negative 90 make negative 30. And so if we divide both sides here by that negative 15, we end up with x equals 2. And so they're just trying to finish solving the equation. So you can see they stuck a 2 into the top equation, which was 5x plus 5z equals 15. So if we want to solve for z, let's simplify that. 10 plus 5z equals 15. We can move the 10 over. We get 5z equals 5. Divide by 5, we get z equals 1. So right now, we know that z equals 1. We know that x equals 2. So then we need to still find the third variable, which is y. And so if we plug in back to our original equations, then we'll be able to get that third variable. So let's go back to the third equation, or the first set of equations. You can plug into any one of those that you like. Let's try and plug into the x minus 2y. So we have x minus 2y plus 3z equals 7. So looks like we have x minus 2y plus 3z equals 7. So we're going to plug in the variables that we know, which are x and z. We know that x was equal to 2, so we're going to have 2 minus 2y, we don't know the y, plus 3, we do know the z was 1, equal to 7. So this will be a 3, so 2 with the 3, that makes 5. So I'm looking at 5 minus 2y equals 7. Minus 5 minus 5, we get negative 2y equals 2. Divide by negative 2, and we get y equals negative 1. So we knew that x was 2. We just got y as negative 1, and z was positive 1. So this is the solution to my system. That's the one point where the planes are all meeting at. Now, if I wanted to check that I was correct, well, that little ordered triplet has to satisfy all three equations. So I'm not going to plug in all of them, so I'm just going to check one of them. So it needs to satisfy all of them. I'm just going to check the third equation. So it says negative 3x plus 2y minus 2z equals negative 10. So I just want to plug in my solution there. Oops, sorry about that. So I'm going to write negative 3 times my x plus 2 times my y minus 2 times my z, and this is supposed to be negative 10. That's my hope. So I plug in a 2, negative 1, and 1. So this will be a negative 6, this will be a negative 2, and a negative 2, which does equal negative 10. Yay. Now again, I only checked it in the third one. You could check it in 1 and 2, but it should be satisfying all of those equations. And that's the main process for solving a system of equations in 3 variables.